So it's a pleasure to be here and to speak to you on the virtual brain and how it's being constructed and how we can apply to disease. But I wanted to take the liberty of putting it into a wider and a more theoretical context and concept, actually, given that we are here at the Mediterranean Seminar for Consciousness. And I thought it would be of interest to this particular group. I usually don't do it to this degree of theorizing in terms of presentations. However, I think it's useful, at least for this group, if we can embed data-driven brain network modeling also in a larger context. Yeah? And for this, when talking about consciousness or about brain states, one theme is a very important one, and that's a theme of emergence. And when talking about emergence and self-organization in complex systems, what comes to mind are several pioneers that have moved forward the field, and I'm plotting some of them here. I'm showing you some. Hermann Haken, for instance, a mathematician from Stuttgart in Germany, who has worked in synergetics and coined the term synergetics. That's the discipline or the knowledge of how elements work together in order to provide an emerging behavior. Ilya Prigogine has taken an approach. He was a chemist working on autocatalytic reactions in particular, and has received the Nobel Prize for the description of this type of dissipative, of this type of emergent structures. Very similarly, in fact, in terms of methodology, but taking a different concept in neuroscience, is Carl Friston, whose free energy principle has become very popular over the past 10 years. And there he's taking actually concepts motivated by stochastics and probability theory, in particular Bayesian inference, that is also describing the emergence of such structures. And what I would like to do is, I'd like to take a few minutes to put it into the context of information theory, and here motivated by the maximum information principle by Edwin James, because it will allow us to connect individual perspectives. And for this, I actually want to phrase it by asking the question, what is actually emerging when we talk about emergence and self-organizing systems? And there I'm making reference to an old review or an old article in the Physical Review of 1957 of Edwin James. And I like it for the reason because he manages to make it very intuitive, linking on the one hand side probability and chance to an interpretation of uncertainty, where actually a broader distribution represents more uncertainty than a short point. Yeah? That provides us already with some intuition. And then what is entering into this aspect of uncertainty are elements of deterministic features. We talk about noise, but also degeneracy. Degeneracy being the property of complex systems, that different configurations can lead to the same outcome, to the same emerging pattern in this context, or actually that the same configuration can actually generate multiple realizations. For the latter, we call this multi-stability. It's absolutely necessary that we have nonlinear systems. Outside of nonlinearity, nothing of this can be accomplished. And the beauty of the maximum information principle of James is that these aspects, determinism, symmetry, degeneracy, stochasticity, drops out very naturally out of the same concept. And the concept is actually that we are maximizing information. And here in this case, we are evoking Shannon's definition of information, where P is the probability distribution of the ith state, K is a normalization constant, and this representation allows us to represent an informatic entropy expression. When maximizing this expression under certain conditions, and in this case, the conditions are the deterministic features, we are actually capable of deriving some probability distribution functions that are representative of the final stationary distributions of the variables that are characteristic of the state of the system. And I don't want to enter too much into the mathematics. I'm providing you the equations for completeness. Take screenshots if you want to. Many of these equations will be known to you from the perspective of Gaussian distributions, second-order moments, or linear systems. And that's the reason why I'm providing this, because I want to connect elements. Yeah. So for us in the real world to interrogate the maximum information principle, the only way for us to do this is via correlations. We measure correlations that then provide us with energy or mean momentum, or an angular momentum. So this type of element that are correlations of individual variables, yeah? And these are typically then expressed as average values, where an expression F, yeah? You compute it via its probability distribution function and you average over the state space, providing you with the measurable quantity. And from the maximum information principle, once we maximize it, we can actually compute the stationary distribution of the probability being a function of the various deterministic features, F1, F2, all the deterministic aspects and constraints that are constraining the system. With a little bit of mathematics, we can then actually derive some of the driving forces, taking some use of very kind of straightforward algebra. Yeah, for this connects unambiguously to thermostatistics. Yeah, when we are looking at equilibrium system, and then providing us with the type of collective variables that we know, such as inner energy, temperature, heat, or entropy in this particular case here. Yeah, so there is a connection that we can make. Yeah. This is the approach of the maximum information principle. And what I'd like to do is I actually boil it down to some of the very absolute basics. And for this, we can actually look at a linear system. We have one single state variable, and the system is a linear system. Essentially, it has a fixed point. X is our variable. This is a state space. And a linear system can either be stable, what you see here, all the flow goes towards the fixed point, or it is unstable, what you cannot see here because I'm not plotting it here. Yeah? So, but in this case, we have a stable fixed point. This is all that can happen in a linear system. And if we, from this, we can actually compute for a linear system, we can compute its potential, and then compute from this explicitly the probability distribution function analytically, so there is no ambiguity. And once again, for a linear system, this provides us immediately with a Gaussian. So you have this Gaussian distribution function, and you have only non-zero first order and second order correlations. These are the first and second order momenta. All other higher order correlations don't exist. We know this. This is second order statistics. Make a note, nothing else can happen in a linear system. Also, nothing else can happen in a linear system if we go to higher dimensions. Same system as before, linear. I'm adding a second variable, again linear. Then we have correlations more, but still to second order. Yeah, but we can also have mixed terms. Yeah, again, we can compute everything that is in the system unambiguously, probability distribution function, and again, a Gaussian term, and this time a mixing term. And we can interrogate the system by measuring all the correlations. You know, these are the mean values. And if the system is uncoupled, then the cross correlation of the two variables is 0. And it provides us, when we measure, make the measurement, with a beautifully symmetric Gaussian curve. And again, we could compute the two-dimensional potential, which provides us the dynamics that is being governed by all the deterministic features. I can now turn on some coupling between X and Y variable. And when I do this, look, what you see here is in the equations, coupling term entered. Yeah. Then it generates non-zero correlations. And what it does is it deforms the Gaussian probability distribution function. So this is what coupling does. It introduces a symmetry breaking and breaks the precedent symmetry. I can again compute the probability distribution function and the potential. And actually what I can do is the explicit form, because I can compute it analytically, I can separate it and rewrite it such that I have a conditional term that is linking Y and X, and having another term that is the independent Y distribution. What I have done here is I linked it to Bayesian formulation of the conditional probability, and joint probability equals conditional probability times the distribution, probability distribution of the Y variable. This is the free energy, in other words, of the system, and is actually the consequence of the symmetry breaking term here that you have in the system. So free energy, you know from Carl Fristen's work. And what it does is it's representative of the coupling of the two variables here. And when we go now away from the linear system, and that's all I'm doing, bear with me, please. From the linear system, I'm introducing now a nonlinearity. So nonlinearity means I will have multi-stability. So the system now looks as follows. We may look at this one. Here we have the corresponding mathematics. You see it's nonlinear. This here would have been, so X and Y, and this here would have been the linear system you just have seen. But if the system were one-dimensional, so we have only one variable, we would see a down state and an up state. Yeah. The fact that I have the system coupled means a second variable, I have a down state and an up state. And now these two systems can interact. If the system were linear, I could describe it by a Gaussian probability distribution function, which is what you see here. But because the system is nonlinear, multi-stability is possible, and I have two maxima of the probability distribution functions, or if it were potentially would be two minima. Yeah, so we have a nonlinear landscape. And when I change the coupling G here, I can actually make it smoother and smoother. And what you see is the maxima become less pronounced until I get the system completely uncoupled. And then you have a certain symmetry here, as is represented here. No maximum exists. However, the symmetry that is in the system, it expresses itself. And if I had noise here, you would be essentially going from one high state of probability all around in the circle here. So this is, as I promised you in the beginning, symmetry is reflected here. And when we turn on the coupling, we go from here to here. It starts shaping the flow. But please recognize that you still see here on these elements here, features of the circular symmetry in the fully symmetric case. And you have a symmetry breaking is actually shaping this flow here. We call this actually structured flows on manifolds, this being the circular manifold, and with the flow on it, exploring with the flow essentially shaping the structure on the circular manifold. What I can do now mathematically, again, I can rephrase it in terms of Bayes formulation. This mathematics completely, in this special case, even though it's nonlinear, I can again compute the free energy explicitly. And as in the previous case, it turns out to be actually the flow on the circle. Said differently, the lawfulness of the behavior that we have here corresponding to the flow on these manifolds corresponds actually to the maximization of the free energy in this case. It's this term here explicitly. And this is a concept that has been used in behavioral neuroscience quite a lot. And I'm addressing now the question actually, what really matters? In behavioral neuroscience, an aspect, it's very difficult to reduce behavior, meaningful and interesting behavior, just to a state. Yeah? So you need to have the dynamic features thereof. And that has actually led to the formulation of structured flows on manifolds, manifolds being low-dimensional subsets, and the structured flow being the lawful behavior. Once the dynamics contracts on the manifold, the structured flow is a deterministic feature that prescribes lawful behavior on the manifold. Yeah. And this can be generated by network and is being actually used by a large range of approaches in the field, in behavioral neuroscience, in the field of coordination dynamics, in fact. Yeah? And when we look into networks, here I'm pointing out our neuron paper, this can be actually systematically generated by large-scale brain networks. If we have fully symmetric coupling, mu equals 0, you see that all the nodes are completely symmetrically connected. Here, I'm doing this in a cartoon. You see that there is an arbitrary manifold, which is actually determined by the interaction terms, but there is no symmetry breaking. So all the flow goes down to the manifold, but there is no, so once on the manifold, there is no action on the manifold. There is no structured flow on the manifold. And then you break the symmetry, and then structure occurs. Here you have a limit cycle. Here you have an object that separates the limit cycle from a fixed point and another fixed point. So the symmetry breaking can actually generate structure on the manifold. And these are the elements I want to conceptually get across. A low-dimensional attractive subspace is described by a manifold, often can be represented as a surface. And then the symmetry breaking in some features of the network generates a flow on the manifold, which actually corresponds to the, when you look at it probabilistically, to the probability distribution function that is being obtained from the maximization of the free energy, as in Carl Friston's free energy principle. So we're talking very fundamental approaches to an understanding of what a structured flow in a manifold is. One more time, the same story, two variables, x and y. Here you have the symmetry, once again, and I break the symmetry. And when I break the symmetry, what happens is that the flows, the right-hand sides of these equations, don't overlap anymore. That's a symmetry breaking. And where they interact, they provide us actually with fixed points. And one of them typically then is unstable, that's this one, flow goes here, and the other one is stable. We can actually put this into mathematical equations and then perform some simulations. That's the identical system that I just explained to you, where the two the null clients, they're called, the flows overlap, and then I break the symmetry a little bit by this term, which will be the output of the maximization of the free energy. And what it does is actually, here we are running simulations, dynamics goes down, goes to a stable fixed point. In red, these are the stable fixed points. If we drive it by noise, what is typically what you see is the system is actually sampling the manifold, following the structured flow on the manifold, but it's performing a sampling. So these are concepts that can be carried into higher dimensional spaces. Here you see a simulation coming from a 20-dimensional network. And the manifold in this case is, again, 2-dimensional. Actually, it is a sphere. Here, now I'm plotting it with a representation of the manifold. 20-dimensional system, dynamics collapses on the object, which in this case is a spherical manifold. And structured flow is being generated on it as a consequence of the deterministic features that are in the system. And the flow becomes actually the emergent object that is being generated by the network. And it can take arbitrary forms as a function of the symmetry breaking. Arbitrary forms means you can have multi-stability, you can have multiple fixed points, you can have limit cycles. So these are all mathematical representatives of what is happening in the system. Yeah. So, and that was actually the key message I wanted to get across in the beginning. So what is it that actually emerges? Yeah, as a consequence of these interactions between deterministic forces, stochastic forces, symmetry, multiplicity that is being brought forward by degeneracy. And the answer is structured flows on manifolds. Yeah, they can be, of course, reduced to, if you would look for a state, then there's going to be only one fixed point on it. Yeah, but they have higher order features that cannot be taken into account by just simplistic linear approaches. And this is what we do with the second order statistics. And keep this in mind, whenever you make a Gaussian approximation, yeah, you're actually approximating it linearly. This is also the other aspect I wanted to show you in the beginning. Yeah. So now let's carry this into real world application. And the link to virtual brain modeling is actually, in this context, that the symmetry breaking of the network is provided by the connectome itself. This is a data-driven approach. In these previous ideal situations, I showed you the fully symmetric combinations would be an all-to-all network. So everyone is coupled with each other, or a zero coupling. Yeah. Don't have this. We have a symmetry breaking. This symmetry breaking we extract from the imaging data by estimating a connectome. Connectome means it's a countable, complete set of connections between individual network nodes. And this we can image for the individual human being. Can image it also for the mouse. There are mouse studies running. But here we will talk only about the human, extracting it from typically the MRI scanner, providing, in fact, a patient-specific or an individual personalized connectome that allows us to be reconstructed. And the way we reconstruct it is twofold. Doing diffusion imaging in the MRI, we can actually extract the diffusion tensor and from this reconstruct so-called streamlines that allow us to make a constructive estimation of the connecting fibers between brain areas. From the anatomical MRI, we can reconstruct the cortical and subcortical surfaces. We have to make a parcellation in order to map it upon a network. Yeah, then we can actually co-register this. Yeah, so here you have a representation of the co-registration process. This is the topology, the connectivity. Here you have the topography, which is the geometry, essentially, the network parcellation. You put it together in the same physical space, in the same topological space, and then you unfold it in the physical space. You can actually equip it with a mathematics, the type of mathematics that we have discussed. A classic system is this bistable network node that I showed you earlier in the system. When you apply statistical physics methods to single neuron dynamics and compute the so-called mean fields, you can extract so-called neural masses. These neural masses are representative of the statistical average of the mean activity of firings, neuron firings, and the mean membrane potential in a network node. This provides us with a dynamic set of equations that we looked at earlier, now here constrained by the connectome. At the position X, we have a network node, which we equip with these neural mass models. And then we can have, for high resolution and nearest neighbor connections. And for from the diffusion weighted tensor imaging, we can extract the connectome, which is then connecting the space or the point X prime to the point X and communicating across the network. This is the mathematics that is behind that. So let me summarize. We extract the cortical and subcortical surfaces, we reparcellate them, we represent them by neural masses, these are the network nodes. Then we connect them by the extracted connectome. And because they are spanned in physical space, we can now simulate them and run simulations. One element that is very characteristic for the virtual brain is, since we work with anatomical data, we can actually, in case of epilepsy, for instance, here, so-called stereotactic EEG, that measures the activity across all different sources. So we have to make the distinction between source on the one hand side and sensor space on the other. And the sensors can be also EEG, MEG, or fMRI. And if you're more interested in some of these details, I invite you to look at the virtual brain platform itself, either directly on the virtual brain platform. I'll show you the website on the next slide. EBRAINS, where you have all the workflows that are existing, connecting the data processing pipelines within EBRAINS. You can actually access them. And here you see the graphical user interface. You can actually connect, you can actually modulate and manipulate the connectivity the way you need it. You integrate the connectome, you span it. If you want to deal with lesions, you can actually lesion it in this environment, or you can actually go to these highly symmetric cases to test hypotheses, as I showed you earlier in the toy problem simulations. You have user interface to control the neural masses and set the parameters. You have high dimensional parameters. And you can set the simulations, you can then set them up and run them on batches directly in EBRAINS on the high performance computing facilities that are available. And here you see two examples. This is on the sensor space, EEG, and this is in the source space, the activity, then generating type of activations in the way you know it from experimental data. So this is an example in sensor space for EEG. Simultaneously in source and EEG and MEG, fMRI, etc. So this does not add any more complications. So that's the environment that I invite you to look at in more detail. It's completely open source, and you can either run it on your workstation laptop in reduced form or take full advantage of EBRAINS. So what I'd like to do is now take these theoretical concepts we started off, structural flows or manifolds, take advantage of an understanding that they can emerge. These are dynamic objects. These are not just states, but they can actually describe dynamic processes in a full and complete form and can be linked to networks. Yeah, and the key driving example that has kept us busy over the past almost a decade has been epilepsy. A few words on epilepsy. So epilepsy is a severe disease that affects 1% of the human world population. 60% approximately can be treated via medication. The remaining 30 to 40% need to be treated differently. And the standard treatment at the moment is epilepsy surgery. And for this, epilepsy surgery means some epileptogenic brain tissue needs to be surgically removed. And for this, you need to know where to perform the resective surgery. And for this, we perform a so-called pre-surgical evaluation using stereoelectroencephalography, which is composed of individual needles, as you see represented here. They are typically 10 to 15 centimeters long with 10, 15, or 20 electrode contacts on there. So these are macro contacts as opposed to micro contacts, which show you more cellular activity. You enter and measure in the volume of the human brain. This is the type of activity that you can actually then obtain from the measurements. There are standard implantation schemes. This goes, for instance, deep down into the amygdala. And this is the type of recordings you can observe pre-ictal activity, some pre-ictal spikes, seizure onset with very fast discharges evolving over space and time. Epilepsy surgery has not improved its success rate over the past 40, 50 years. It depends on the type of epilepsy, but overall, it remains at about 60, 65% of success rate. So the workflow we use in the Human Brain Project, taking advantage of this virtual brain technology, is the following. We reconstruct individual patient data, connect them, span it cortically and subcortically, register it in the same space, equip it with the neural mass models, and study and simulate the dynamics. Typically, we refine it with additional information, so-called prior information we have for a particular patient. This can be a lesion or a hematoma that is visible in the MRI. And then we perform so-called model inversion. There we are taking a Bayesian inference approach where we are estimating the parameters of the virtual brain model for the particular patient. In the case of epilepsy, in this case of this pipeline, it is the epileptogenic zone, the location of the epileptogenic zone, which then directly translates into the target for surgical interventions. So I'm connecting now to the beginning of this talk, actually. Here I'm showing you a seizure, which is actually in toto, so the hippocampus of the rat, extracted. Timescale is multiple minutes. So you see pre-ictal activity and then seizure. And this particular seizure lasts 30, 40 seconds, then it saturates, stops, and it repeats itself. This can be mathematically actually described by a so-called fast, slow system. Yeah? The mathematic, or here you see it in the simulations. Yeah, fast, slow system. So it's an alternation of fast and slow periods. Mathematically, it translates fundamentally on the mathematical object, on the structured flow on manifold, which has here the rest period. This is a period we would like to have stabilized, the inter-ictal activity, and then it destabilizes via so-called bifurcation and goes into the highly oscillatory mode, the seizure. Yeah? This spiral is the mathematical object that we're talking about, the structure flow on manifold, and this can be unambiguously characterized by bifurcation. So destabilizing of this resting mode, going into the spiral, and then an exit bifurcation. And there has been loads of activity for the past 10 years trying to extract this out of the data, characterize it mathematically, and I'm just highlighting some papers here. In particular, this one was the first paper that actually described this mathematical object as being representative for seizures. Yeah? And the trick that has been chosen there is actually mathematically, there is only a finite number of bifurcations. So the type of onset to go from a steady state into an oscillatory state, from oscillatory state to a steady state, there is only a finite number that you can actually classify systematically. We call them bifurcations. They have different properties in terms of amplitude, frequency. They can go from rest to seizure only, or they can be bidirectional. So this property, we can actually span it in terms of onset and offset behavior and arrive at a taxonomy that allows to systematically classify seizures by this new mathematical object in terms of structure flows or manifolds, and characterize it in a so-called dynamotypes, where they are like a periodic system of chemical elements. It can very systematically described by very detailed properties. This can be applied to human data. In this case, this has been done with Pill Stacy to a set of more than, actually, this has been more than 1,000 seizures, about 130 epilepsy patients that have been recorded in DC, actually, which renders this data set unique. The DC recordings you see here. And then this would be the AC, the filtered recordings where the DC shift has been removed. We can actually classify, according to this taxonomy, the different seizures, make very detailed predictions, which one can actually be stimulated, which one cannot, because you need to have bistability. So based on the dynamotype. And another element that comes out of this is that actually, look at this pinkish color here and the blue color, which together for the onset bifurcation, they are both saddle node bifurcations. They determine 80% of all seizures fall into this category with onset bifurcations. And for the offset bifurcations, you have the so-called homoclinic type that falls into this category. So we have dominant classes of dynamotypes and less dominant classes. And that can allow us actually to formulate this mathematically and put it together and equip the virtual brains of patients with this structure. Yeah? And we can actually estimate it. We can actually go into human virtual brains and start the process called sampling, perform model inversion and estimate their behavior and estimate actually where the epileptogenic zone is. This object here, I told you, is a corresponding epileptic structure for our manifold. If we project it, if we don't keep it in 3D, but project it into the two-dimensional plane here, you see that this is a resting state of the, if you wish, healthy non-ictal state. And here the projection becomes this accumulation of many data points here if a brain area goes into a seizure. Now, you can actually start mapping this out using SEEG data. And actually, here you have the corresponding time series. And here you have the projection into the X and Y space. You see this here, when you look at the numbers here, -2, -6, 1.6, it's actually located somewhere here. It's not sampling the entire area. It's located here. So this is not seizure. Another brain area, not seizure. And this one is clearly seizing, going from the non-ictal to the ictal state. Yeah. So this we can actually systematically map out. And then we can actually map across different nodes the degree of the epileptogenicity. Yeah. What you're having plotted here are the posterior probability distributions for individual areas. Here you have it mapped out for all the network nodes, so about 164 brain areas. But let me zoom in those that are relevant, and in particular when they are epileptogenic. So these are that pass this line here. You have a representation of this here. I'm sorry, you cannot read the region names, but look at the following. Being in this area here, it's epileptogenic. Please recognize the following. Sometimes they are multimodal, as we saw it in the probability distributions in the beginning. A Gaussian approximation for a posterior multimodal distribution would provide you with something that looks like this. I'm taking one posterior multimodal distribution and I'm plotting it here, as you see. And if we perform so-called variational inference, so making a Gaussian approximation of the parameters, we're estimating the red part, which is completely different from actually what the reality is. It works well for another network node, but it doesn't work at all for this. Anytime you do second-order statistics, it does not mean that you're doing an unbiased estimation. It means that you're actually assuming an underlying linear model, as I explained to you in the beginning, and then you're plotting the much higher detailed features that you could have because of the nonlinearity. You're estimating by a linear model, and you're getting absolute garbage out of this. Yeah. However, here in the context of epilepsy, we cannot afford that. And we have to use very higher order approaches such as Monte Carlo Markov chain approaches, where we need to actually sample this manifold. As I showed you in this very trick simulation earlier, you can actually sample these manifolds, which is extremely time consuming and requires higher order, high computation, high performance computation resources and supercomputers. This is where much of the time goes in there, the differences between this Gaussian approximation versus a real sampling of the surfaces. Let me not talk about the other elements, but let me show you some results as I'm getting to the end of the lecture. What we are sampling is, through this approach, we want to sample the parameters, so we're estimating the parameters. In this case, a so-called heat map. For this particular patient, it's an estimation of the distribution of the epileptogenicity. This is before surgery. We pass on the information of this estimation to the surgeon. They evaluate in the staff meeting. And for this patient, it's after the surgery, actually. So this is the target for the resective intervention. Big advantage of the virtual brain is that you're not providing just a mapping, just another index where the epileptogenic zone is. There are a few available on the market, and the virtual brain works very well. But you can actually take the virtual brain model and then run simulations. This is what we do on eBrains. In blue, you see the individual brain areas, and they are running. We run a simulation, and then we map the activity on the SEG sensor as we do it, as we collect it in the empirical data. And here we are simulating a seizure for a particular patient, seizure onset in these areas. And these are the SEG data that are being plotted. It's evolving. You see a spatiotemporal characterization characteristic for this patient, evolving, recruiting some other areas, and then at the end, seizure offset. So we can use the estimated parameters also to perform questions asking about, what if I perform surgery here? Will I cure the patient? How can I intervene alternatively via stimulation, etc.? This is happening right now, this type of research. The mapping is actually being tested already in a clinical trial, which started in 2019 with 400 prospective patients. Prospective means that the actual mapping of the epileptogenic zone in the virtual brain is being taken into account in the decision-making. In this case, it's 13 epilepsy centers in France. We centralize all the data. We anonymize them. We send them to Marseille. We perform in Marseille the virtualization, the estimation of the epileptogenic zone for each individual patient. And then we send it back to the clinical decision-making, the staff meetings at the clinics. First results are available. We have, by now, we are almost halfway when I say 400. So 172, that was in June. So I think we had around 200 patients now, of which half of them have been randomized, which means half of them will receive, one arm will receive the information about the virtual brain EZ, epileptogenic zone mapping, the other one not, because we need some control groups. And in terms of performance, this is what it looks like at the moment. We can, when we virtualize the patients, we can either compare it directly against the clinical hypothesis, and then perform how well does the virtual brain estimation do when compared against clinical hypothesis. We can compute a battery of metrics. AUC, you may know, for instance, if you see AUC metric there, we had around 76% precision and recall. So this is a specificity and sensitivity. This is across all 53 patients that we have at the moment. This against clinical hypothesis. If we go against post-surgical MRI, as I showed you earlier, we can actually split 12 non-seizure-free patients, seizure-free patients, and 13 patients are non-seizure free after the surgery. This is one of the indices that the clinicians typically use, epileptogenicity index. This is clinical hypothesis. VEP, this virtual epileptic patient. So you see for the seizure-free patients, so for the success patients, it remains comparable. Precision is a specificity against what surgery has been actually performed. If we compare against non-seizure-free patients, actually it drops dramatically for VEP, also for the others, but most dramatically for VEP, in fact, which is indicative for actually that there is maybe some predictive power in terms of the surgery correctness or the surgery success linked to a good mapping out of the epileptogenic zone. Yeah. So let me stop here. What I wanted to share with you is theoretical concepts, introduce you to the virtual brain and its applications in the context of epilepsy as we do it in the Human Brain Project and using the EBRAINS platform. Very importantly, there is the lead of the theoretical concepts by means of structural flow and manifolds is a mathematical object that is non-stationary. It provides us a good mathematical foundation that we can actually estimate through higher order techniques, in this case through Monte Carlo Markov chain techniques that can be run and used on eBrains. If we had chosen other smaller techniques, as I wanted to try to convincingly show you, if we had made the Gaussian approximation via variational inference, it would not work. Yeah, and here we are having some success examples where it's actually going in the right direction. I thank my colleagues, in particular the clinical team, Julia and Fabrice and Maxime, and I also thank the funding agencies. Thank you very much for your attention.